Hello everyone, welcome to my civil engineering YouTube channel. Please subscribe to it and hit the bell icon to get notified when I post my new videos. Today I'll be discussing a numerical on stress, strain and Young's modulus. So in my previous lecture series I had discussed the concepts regarding stress, strain and Young's modulus. So you can just go to the previous lecture series for the reference. So in this video I'll be discussing a numerical which is a very important numerical in this concept. So this is as follows. So the following data refer to the mild steel specimen tested in the laboratory. So they have taken a mild steel specimen wherein they have tested in the laboratory under universal testing machine. So initial diameter was found to be 25 mm, length was found to be, that is initial length was found to be 300 mm. So these are the dimension, that is 25 and 300 mm was before the application of the load. So extension under the load of 15 kilonewton was found to be 0.045 mm. So as soon as the load of 15 kilonewton is applied, so there was some extension that is found to be 0.045 mm. So here they have given extension, that is nothing but the stretching of the material. So here whenever the dimension increases, so you can just assume that along that dimension there will be the load application, wherein if at all if there is stretching of the material, then it is subjected to the tensile load, and if at all if it is shortening of the dimension along the load application, so it is subjected to compressive load. But here there is the extension under the load, so wherein you can just take it as the tensile load itself. So next is load at yield point. So that load is taken as 27.65 kilonewton. So at that point the material starts to yield. So next is the maximum load, or it is also called as ultimate load. So wherein the material takes the maximum extent of the load it can service. So that is 208.6 kilonewton. So the next thing they have given as the length at failure. So that is 375 mm. So you can just observe initial length was 300. So length at failure was 375. So by this you can just take it as the length, as the load is applied along the length, the dimension along the load application increases, but the dimension perpendicular to the load application always decreases. So therefore here you can just observe the initial length is 300, which is less than that of the length at failure, but the initial diameter is 25 mm, but the neck diameter or the diameter at failure is 17.75. Therefore here the length or the dimension along the load applied is increased from 300 to 375, and perpendicular to the dimension is decreased, that is from 25 mm to 17.75 mm. So this is the concept. So next is they have asked to find out the Young's modulus, yield point, ultimate stress, percentage elongation and percentage reduction in area, wherein they have given the factor of safety of 2, and they have also asked to find out the safe stress. So the first and foremost step here is to find out the area of the material. So since they have given the diameter, so it is understood that if the diameter is given, then it is a circular cross section wherein the area is taken as pi d square by 4, wherein d is 25 mm. So pi into 25 square by 4 is taken as 490.87 mm square. Since d is taken in mm, so therefore area is equal to 490.87 mm square. So the next step is calculation of intensity of stress. So first requirement in the problem is they have asked to find out the Young's modulus. So here we are supposed to find out the Young's modulus. For that for finding the Young's modulus, we are supposed to find out stress and strain. So therefore, I have found out the area first. So after that, I need to find out the intensity of the stress. So as I know that stress is nothing but load by cross-sectional area. So load by cross-sectional area is nothing but the stress, but as we know that the Young's modulus is nothing but the ratio of stress to strain within the elastic limit. So here in the problem they have given the load at yield point as 127 point something. So here they have given the load at yield point as 127. You can just observe here the load at yield point as 127. The extension under 15 kilonewton is 0.045. Means this is understood that the load, the material starts to yield at 127.65, but below the 127.65, the load below 127.65, it is called as elastic load. So wherein the Young's modulus has to be found out within the elastic modulus, within the elastic range. So therefore, in order to find out the Young's modulus, we are supposed to take the load as 15 kilonewton itself. So we are supposed to take the load here as 15 kilonewton itself. So 15 into 10 power 3, that is I have converted kilonewton to newton. So therefore 15 into 10 power 3. So divided by area of cross section, just now we have found out it as 490.87. So therefore stress is taken as stress is calculated as 30.55 Newton per mm square. So the next is calculation of strain here. So here strain is nothing but change in dimension to the original dimension, but here since it is subjected to tensile load, the change in dimension in particular is nothing but the elongation, or it is also called as stretch. So stretch divided by the length. So stretch under the elastic load we are supposed to take here. Why? Because Young's modulus is nothing but stress to strain within the elastic range. So therefore the stretch at elastic range we are supposed to take, that is nothing but stress at 15 kilonewton load, that is they have given as 0.045 divided by the initial length, that is 300. So therefore I have got the strain as 0.15 into 10 power minus 3. So it is constant, so it should be remain as it is. So the next is calculation of Young's modulus. As we know that Young's modulus is stress to strain within the elastic limit. So here stress I have got it as 30.55 and strain I have got it as 0.15 into 10 power minus 3. So therefore after simplification I will get the Young's modulus as 2.03 into 10 power 5 Newton per mm square. So the next requirement of the problem is to find out the yield point stress. So yield point stress is nothing but load by cross-sectional area at yield point. So yield point load divided by cross-sectional area. So yield point load they have given as 127.65 kilonewton. So we are supposed to convert that kilonewton into newton by multiplying it by 1000. So therefore it is 127.65 into 1000 divided by the area of cross section that we have calculated earlier, that is 490.87. So therefore stress is equal to 260.04 Newton per mm square. So this is nothing but your yield point stress. So next is calculation of ultimate stress. So here they have given the ultimate load. So ultimate load by cross sectional area. So ultimate load they have given as 208.6 in the question itself. So it is in terms of kilonewton multiplied by 1000. So it will be in terms of Newton. So divided by cross-sectional area, the same cross-sectional area should be taken into consideration. So therefore stress after simplification I have got it as 424.96 Newton per mm square. So the next is percentage elongation. So it is nothing but initially the length is less than compared to the final length, as it is subjected to the tensile load. So therefore I need to find out the percentage elongation. So therefore it is taken as length at failure minus the initial length divided by length at failure into 100. So length at failure I have got it as 300. So divide minus initial length. Initial length here it was 300. So here it was 300. By mistake I have typed as 200. So sorry. It is 375 minus 300 divided by 375 into 100. So therefore I have got the percentage elongation as 46.67%. So next is percentage reduction in area. So as I said in the beginning of the problem itself, as the load is applied along a dimension, the dimension along the load applied will be increased when it is subjected to the tensile load, and the perpendicular to the load application, the dimension perpendicular to the load application is decreased. So therefore as in this problem, with respect to this problem, the length is the load is applied along the length, so the length is increased, and the perpendicular dimension to the load application here is diameter. So therefore the diameter will be decreased here. So therefore initial diameter is more compared to the final diameter. So therefore we are supposed to find out the percentage reduction in area. So wherein final area I am supposed to calculate. So final area by using the neck diameter here. So final area is pi d square by 4 again. The same formula. Here D will be 17.75. That is nothing but the diameter at necking or diameter at failure. So I have got the area at final area as 247.44 mm square. So next is percentage reduction in area I need to calculate. So here initial area is more and final area is less. So initial area minus final area divided by initial area into 100. So initial area with the 25 mm diameter I have got it as 490.87. Final area with the diameter of 17.75 I have got it as 247.44. So divided by initial area, that is 490.87, and multiplied by 100, I have got the percentage reduction in area as 49.59. For watching, please like, share and subscribe. Thank you.